This is my extreme oscillator with 21 crystals in parallel. I have just connected it to my test system, and you can see how the frequency is approaching something near 10 megahertz. And you can see the baseband graph, how the automatic frequency control is trying to move the signal into the filter, but fails all the time, but gradually not so much. What you see here is what it looks like when I have the Wenzel oscillator connected. And you can see here when it shifts frequency again, fairly soon, I think. Right there. The power into the oven is constant all the time. So the decreased speed for frequency change, you can see, is because the temperature coefficient of the crystal approaches zero at the magic temperature. What you see here is that I had fed it with 18 volts, so I adjusted it to 16 volts, which is the nominal voltage for my experimenting. The phase noise at 1 Hz offset is very low. You can see the blue traces here at minus 130. Blue means that the real part is negative. So it hovers around minus 130 dBc per Hertz. But there are problems, there are glitches occasionally, and there is also a problem with my channel 1 oscillator, which is far more noisy than the one in channel 2. And now that I can see it, I can perhaps do something about it. And here you saw there was something, and I think it was in channel 1 that I could see down here. But I didn't look while it happened. But the event has destroyed the good performance. Now it is minus 100 and maybe 25. So there is some work to do. And there could be a problem in the 21 crystal oscillator also, because all the oscillators have bad polystyrene capacitors. Now that I have studied capacitors and found what to use instead of the Chinese one I have been using, I will replace them while looking at what happens while doing so. The frequency is slowly getting constant. The thermostat oven for the crystals has reached equilibrium quite some time ago now, but the box is warming up very slowly. And that changes the frequency because it's only the crystals that are temperature stabilized. The rest has room temperature. Here is frequency versus time. It's obvious that the green trace is far more noisy than the red one. So to make this work easier, I have to fix the oscillator before working with the 21 crystal box. Now, since the problem is only in one of the reference oscillators, it shouldn't affect the correlated spectrum, the yellow and blue trace, but it makes the measurement time much longer. So I wait to see what the average will become here. Despite these problems, obvious glitches, the phase noise seems to be somewhere around minus 130 dBc per Hertz. Frequency versus time, you can see the green trace, it is quite ugly. So I will fix that before continuing. I have hit the channel 1 oscillator with a hammer. The frequency has jumped over 20 millihertz, so I have to adjust the trimmer on it. I have hit the channel 1 oscillator with a hammer. The frequency has jumped over 20 millihertz, so I have to adjust the trimmer on it. Suddenly there was a problem. You see this line here. I see here that this was an amplitude spike of some kind, and it came here also. Could come from anywhere, connectors or the oscillators. I don't know whether it was in both. If it was the multicrystal oscillator, it would come in both channels. If it is the channel 1 oscillator, it should come only in channel 1. But I didn't look, so I don't know. Anyway, a little better is now. I think I have gained something like 4 dB on the green trace. I don't remember exactly where it was. 1 Hertz offset would be somewhere here. 128. It would probably go down if I wait for a while, because the imaginary part is right in the middle, and I have negative values even here. 1.5 hours. I can read minus 132.5 dBc per hertz at 1 Hertz offset. But there have been glitches, and they are in the amplitude. And I don't know whether it is where it is. I will make a lapse rate recording so I can see that. But it means that the oscillator with 21 crystals is better than minus 132 dBc per hertz. That's really very good. I have a look at amplitude noise. It is very low. Even though I know there are pulses in the amplitude, and I can see that because this effect is from the digital filter in the sound card that I'm using. It is an algorithm that makes the DC component 0, and it changes as there are changes in the amplitude of these strong signals. I don't know what conclusions to draw of this. It looks like noise. The signal to noise ratio is not very good. You can see the imaginary part is at the same level as the real part. I need to have a better channel 1 oscillator. I have cleaned the cables between the Schottky mixers and the audio amplifier in my 2-channel direct conversion receiver, because I think that the problem I saw in channel 1 was caused by poor contact in that cable. And now I'm collecting phase noise again, and we'll see if that problem comes back or if it is gone now. It looks very promising, however. 8 averages, minus 132 or so dBc per hertz at 1 Hertz offset, but very uncertain so far. There are still glitches, this one, not visible here, so it's a narrowband thing. It could originate in the 21 crystal oscillator, which uses these cheap Chinese polystyrene capacitors. I will replace them when I am finished with this investigation on the channel 1 oscillator. This event was in channel 1. You could see it just there, and it's fairly strong. It seems I don't see it in the frequency versus time graph. I changed the scale. Yes. Here was a jump in the frequency in channel 1. I just wonder the reason for that. It cannot be any of the polystyrene capacitors anymore. It must be something else. It could be a connector problem, of course, somewhere. This event in channel 1 you have just seen cannot be caused by the polystyrene capacitors, because I have replaced all of them with good capacitors from LCR. So this is something else. The camera sometimes doesn't save the videos I make, so when I told you that I had replaced capacitors, that one has disappeared. Here is a time-lapse recording. I started now, and you can see how the noise goes down around minus 132 now. There are some events here, and I will stop and show what they are. Here is one event. Stepping, you can see in the baseband it's channel 1, and you can look here. It doesn't have much effect on the, what you see. The green trace went up just a little. It is the average of 400. So adding one bad one doesn't change the average much. Here comes something that looks more ugly. You can see the yellow trace at minus 130.5, and while I step through this event. It starts, look here, a strong structure, but no, very small effect. You can see here it comes, but a couple of tenths of a dB only. Because this happens in the channel 1 oscillator and not in channel 2. And here comes something much stronger. Look at the yellow curve, and also in the baseband. More than 20 decibels above the normal sideband noise level. And you can see here, these are red, because Linrad decides that this is not really what we want to worry about, so it doesn't collect the average of this, or only fractions of it. The average correlation is at minus 130.5 now, and I look through the baseband while stepping here. 20 decibels above normal, and several frames, 30 decibels, and even more. Look here, these are red now, means Linrad doesn't collect average spectra from this event. And it continues. Nearly 40 decibels excess noise. And it has lifted the yellow trace a little bit, but not very much. And it goes on like this. Now there is another kind of event here. Look at the yellow, minus 131. And I step, you can see in the baseband. Here, it is a white trace surrounding the peak, means it is the same in both channels. It means it is correlated and it will be strong in the yellow spectrum and degrade performance here. And it originates in my 21 crystal oscillator. And I don't know the reason for it, but I have not replaced the polystyrene capacitors in it. Anyway, this is my real test object that has a glitch of some kind. And when I continue stepping, you could see here how the yellow trace jumped up when this interference entered the correlation spectrum. I will insert the entire time-lapse video. It is 1 minute and 34 seconds. correlation spectra have been averaged for 3 hours by now. And here is the lean rod. It says minus 130.5. The PN 2060 says minus 130.4. And this is with the filter. If I removed it, it says minus 130.8. So now, after enough time, lean rod and the PN 2060 agree on the level for the phase noise. The frequency is drifting fairly fast, but I can see now that the green trace is smoother than the red. It means that the channel 1 oscillator is more stable than the one in channel 2. The amplitude noise is lower than what can be measured within 3 hours. It is in the order of minus 144 dBc per hertz at 1 hertz offset, but it is at the same level as the imaginary part of the correlation spectrum. So it isn't really a measurement. For some reason, the power supply is at 17.9 volts. I may have forgotten to adjust it properly. Reducing the supply to 16 volts changes the frequency by 300 millihertz, 0.3 hertz away from previous value. So I reset and of course restart the PN 2060 because that steep change destroys the measurement completely. Stop and restart. I restart the collection of averages in lean rod also. At a lower supply voltage, the heat developed within the oscillator is becoming smaller, so the frequency is drifting now for a while, rather quickly. The Hallan deviation reflects the frequency drift of the oscillator. I go for Hadamard deviation. Here it shows the noise sidebands, and they are very much weaker. So this will be better after some time. I don't know how long, maybe an hour or so. The lock range of the channel 1 reference oscillator is about 4 times larger than for channel 2. I have seen loss of locking due to temperature changes, so I made it this way. To have the same suppression of the noise from the rubidium source, I have increased the time constant at this point in time by a factor of 4 in channel 1, and it will take a lot of time before the tracks join again. Here I waved my hands close to the oscillator to make it more rapidly reach room temperature. You can see that it makes that better. The yellow trace here is the frequency difference between channel 1 and channel 2, and it looks smoother here than it did before. So maybe this was rubidium oscillator variations. Now I think frequency drift is slow enough, about 1 millihertz in 250 seconds. So I reset everything here. Time is 4:30 in the morning. Up in the corner you see 2:32. That's Greenwich Mean Time. And I will leave this while I go to sleep. 9:30 in the morning. The sun is starting to come into the room through the window, and that raises the temperature from have been fairly constant during the night, and now it increases. And you can see clearly that the channel 1 reference is significantly better than the one in channel 2 when it comes to the longer time scale. The Allen deviation at 10 seconds comes as 1.8 times 10 to minus 12. And if I look at the Hadamard, it is very much better, because this frequency drift comes in the Allen deviation. So the Hadamard 10 seconds, 8.8, that's 9 times 10 to minus 14. The correlation between the noise in the two channels is very weak, so this is not a high precision measurement. You can see it becomes negative at 20 seconds. And at 1 second, 4 times 10 to minus 14. Phase noise in Linrad is a little bit hard to read because the curve is jumping up and down by about 1 decibel, but if I try to fit something, it's more or less where the mouse crosses. That's minus 132 dBc per hertz. And of course I can look at the PN 2060. This is with the filtering, moving average filter with 11 pixels for the window size. And it says minus 132.3. And looking at the curve, it's a little bit difficult. I remove the filter, and it says minus 132.6. And I make a much larger filter. The biggest is 51 points. Then it says minus 133.9. Maybe it's about 132 point a little. The time now is 11:45. Channel 2 reference oscillator has lost locking. I designed it with a very narrow lock range of 20 millihertz. Now you can see it is a little bit larger than that, but it's not big enough. So this is not very good. I will increase the lock range by a factor of 3 or something like that. The phase noise I see is maybe minus 132. Still this problem that this curve is not a straight line. If I look at the PN 2060, it says minus 132.7. And I can play a little bit with this filter. It is now window size 21, and I make it smaller. And minus 133. And if I make a very large filter, this is maximum 51 points. It says minus 133.7. And I don't know what to say about this. And I don't want to wait any longer. What I want is to see small changes in phase noise performance in a short time. And to that end, the data you see in this window, phase noise for each new average of the yellow curve comes, it is now minus 136.8. It's the decibel numbers, these values, averaged over the green range, which stretches from 0.5 hertz up to 2.5 hertz. So there are many points, and that means that this average should converge fairly rapidly. Now, this information is available in a text file on the system. The file is DMP1 in the same directory as where I was running this instance of Linrod. And you can see it ends with 3,999 averages at 136.8. And I can scroll backwards, and it doesn't vary much, a couple of tenths. And here at 1,700, it differs by 0.2 decibels or so. I will bring this into Excel and plot it. Here is the average noise over 0.5 hertz up to 2.5 hertz, offset from the carrier. The blue trace is at 16 volts from the power supply. The red is the first measurement, which was close to 18 volts. And this jump is something I did before shutting off, so forget about that. I'm a little surprised that the trend continues for such a long time. It seems there is some similarity. I don't know really what to think about this, but it seems I need at least this amount of data points to have an error that is less than 0.5 dB in the difference between the curves. The endpoint here of the 18 volt at 1,913 averages, and that's a long time. This is about 1 hour, and I can see now that as the flat noise floor of my receive system starts to become important, the signal-to-noise ratio of the phase noise to the receiver noise degrades. So I should not collect up to 2.5 hertz, I should stop at about 1.5 hertz when computing average phase noise. This is nearly 3 hours collecting averages from 0.5 hertz up to 1.5 hertz. The signal-to-noise ratio is fairly good, except at the very lowest here at 0.5 hertz. I don't know if this is some kind of spur or if it is just statistics. We'll see how the average develops over time. It seems I need about 1,500 in order to see reasonably small changes when I do things in the oscillator that might affect the phase noise. I have increased the lock range for the channel 2 oscillator, and I have been running 1,587 averages, and the value I get is minus 131.99 or 132 right now, and I expected 132.15 plus or minus a couple of tenths. So this is good, but there is a problem. You can see the green trace here. The channel 1 PLL has lost locking. Presumably I didn't tune it well enough to absorb the temperature variations I have in the oscillator in a good way. So I will change the channel 1 fixed variable capacitor, reduce it just a little bit to regain locking. I just restarted, and this event happened. And I saw a distinct degradation in the average, because this is a pulse of some kind from the 21 crystal oscillator. It came in both channels. And I guess it has to do with those polystyrene capacitors that are a little unstable and sometimes makes a little jump. I have restarted again after having the oscillator properly locked. And it's interesting, the locking in channel 1 looks much better than in channel 2. It's the same parameters in time and frequency as before, 10 seconds per point, 0.02 in this box. And temperature is doing something here in this room. The phase noise at 1 Hz offset is here. That looks like minus 132 dBc per Hertz, or maybe a little higher, minus 131. Knowing how to draw the line in this not straight line curve is a little bit uncertain. In the logarithmic scale, we expect a straight line, and it looks like minus 131. And I have to go back to the linear scale to get the appropriate value for the average phase noise, minus 131.53 at 1,500 averages. It's a little bit more noise than before, but it could be there was a glitch in the oscillator at some point in time here. It's not alarming, I would say. Now I have collected another 1,549 correlation spectra, and I have this yellow trace, but this time the average of all the points between 0.5 and 1.5 Hertz is not as good as before. It's 129.1. And the reason is here, the channel 2 oscillator has lost its locking. So I will change that. It is not so easy to set the proper level. What I have to do is to reduce the capacitance to get it to lock. The temperature is varying very much. And that is because we have a heat wave here now. Previously, the much narrower lock range did not cause any problem of this kind because I had a constant temperature indoors. Now I'm satisfied with the reference oscillators. I have modified my 21 crystal oscillator by replacing all the polystyrene capacitors by capacitors with tin foil or with welded electrodes. And this is what I see, frequency versus time, and that will be okay for further measurements. The average correlation spectrum shows minus 130 dBc per Hertz. There are glitches, not so infrequently, and despite that I have minus 130, so if I can find the origin of these, I expect the noise to go down below minus 132. The PN2060 shows minus 130.0 at 1 Hz offset. Here is the average of the average correlation from 0.5 to 1.5 Hertz as it develops over time. The blue trace is 1500, or I don't remember, but many more. I started with the red trace, observed a strong glitch, and restarted and then got the blue trace. I had expected minus 131.2 or something like that. So the unit is more noisy now than before. And you can see the glitches as strong ticks upwards like this. So I will clean connectors, the usual suspects, and maybe that's the problem, maybe it is something inside the box. There are still glitches in the box, and that affects the phase noise. Now it is at minus 129 in Linrad. And this is not really what I want to see. Minus 133 on a dip in PN 2060. I go for plot control and enable the filter. And then it says minus 130. Well, I don't want to wait lower because I have an error that I have to correct somehow. There are still glitches in the box, and that affects the phase noise. Now it is at minus 129 in Linrad. And this is not really what I want to see. Minus 133 on a dip in PN 2060. I go for plot control and enable the filter. And then it says minus 130. Well, I don't want to wait lower because I have an error that I have to correct somehow. Here is the current schematic diagram of my 21 crystal oscillator. I want to know whether the glitches I see originate in the crystal part or in the amplifier and limiter part. To do that, I disconnect here and feed a signal into this point through a 470 ohm resistor, because I know the impedance in this point here is 510 ohms. I established that by measuring the current through the crystal in a way that doesn't load the Q at all, with this disconnected. And then I added resistors in parallel until the signal was 6 decibels lower. Then I know I load with the impedance that is the source impedance here. And that was 510 ohms. So 50 ohms of the signal source plus 470 gives 520, close enough to feed the amplifier with a room temperature noise resistor that is the same as the room temperature noise from the crystal. The crystal could have other mechanisms also, I don't know. But anyway, I should be able to see if I have this problem coming and going. I have switched from running as an oscillator to use the box as an amplifier, amplifying the Wenzel oscillator through a 470 ohm resistor. It's clear that the Wenzel is a little bit more noisy than what I have in oscillator mode, but the glitches, if present, should be visible in white up here. And of course, the average phase noise is about minus 120. That's the properties of the Wenzel oscillator. My reference oscillators are a little bit better, so they are less than 3 decibels above the Wenzel. If they were equal, they would be 3 decibels above the Wenzel, as indicated. The yellow is the noise of the Wenzel only. The magenta and green is the sum of the noise of the Wenzel and one or the other reference oscillators. The PN2060 uses the Wenzel oscillator as reference number 1. It means it contains exactly the same phase noise as I send into the box, which means that it cancels. So there is no contribution from the Wenzel oscillator in the result of evaluation of channel 1 reference with respect to the device under test. And therefore there is no correlation between channel 1 and channel 2 for the noise from the Wenzel. And therefore I can see already now minus 130 dBc per hertz. And that is finally the total noise added by the amplifier and by the test system, that is the PN2060. And where that will come, I don't know. After nearly 9 hours, the noise floor in the PN2060 at 1 Hz offset is minus 141 dBc per Hertz. And that indicates that these glitches are not caused by the amplifier. Now I'm looking at the normal output, not the feedback output, so I have to test that as well. It could be that amplifier that is causing the problem. During all the time I have made a time-lapse recording, so I can check in the baseband waterfall here if there are any problems. In Linrad, of course, I don't see anything other than the noise of the Wenzel oscillator comes at minus 120.4 about. And I can see in the frequency versus time that the long time stability of the Wenzel oscillator is far better than what I have on my experimental oscillator. What you see here is probably a change in the mains supply voltage, because the power supply has a fairly bad line regulation, and it's a slow and not very long-lasting event. This is 8 hours on the feedback output. The noise at 1 Hz might be a little higher, but it's questionable. The uncertainty is large here. Anyway, I made a lapse rate video of this also, and I have studied both the lapse rate videos, and there is no sign of glitches in the waterfall. So the problem with glitches is not caused by the amplifiers. I have reconnected the crystals, and here is the transmission from input to the main output. The gain is minus 4 decibels because there is no output amplifier yet, so the 14 dBm input is now 10 dBm on the output side. I have replaced the crystals with an inductor. This has changed the Q from about 1 million to about 85. And gain is now plus 12 dB. So I will feed this with a much weaker signal to get the normal output level on the main output, to see if there is some problem with the capacitors that are used together with the crystals, and now instead with the coil. After 5 hours, this is what I find on the screen. There are obvious problems. I don't think this is the capacitors. It looks to me like there is some self-oscillations going on now and then. The input source follower is seeing a very high impedance now, so it might well be misbehaving. I will have a look at the lapse rate video I made. Here I'm running 10 times faster, so it doesn't take forever to have a look at it. And now it goes back, but not quite to the situation from the beginning. And then there is this noise again, coming and going. And if I have a look at the start of the video, This is clearly better than anything that comes after these interference situations. Here is the time-lapse video. To start with, it looks good. You can see in the baseband waterfall. And the PN2060 goes down. Now it is minus 130. Well, it goes up and down. And now there are glitches, and oops, something very bad happens. The high impedance of the LC resonator caused self-oscillations in the source follower, which has some negative resistance at the input. So now I'm feeding the LC resonator through a 470 ohm resistor. Means that the amplifier is seeing the normal 520 or 510 ohms, and then there are no self-oscillation problems. I will run this with a lapse rate recording for several hours to see if I can see any glitches or problems with this. The noise level I see with the PM2060 is significantly higher than when I fed the amplifier without having this LC resonator in parallel. But looking at the graph, I see the small circles everywhere around here, which tells me that the statistics is not finalized properly. I made a time-lapse recording and I will look at it to see whether there are any glitches. The FSWP may be sensitive to overtones, so I insert this bandpass filter, and it suppresses all overtones by almost 40 dB or more. I'm sending the signal from the 21 crystal oscillator through the bandpass filter, and then to a hybrid that splits it into two signals. One goes to my usual system with Linrad and PN2060. The other goes to an FSWP. After 2 hours and 30 minutes, the phase noise I see in Linrad is minus 131 dBc per hertz. The PN2060 shows minus 131.7. This is with a window of size 3 with the moving average filter. Without any filter, minus 130.3. And the larger filter, this is 3, 4, 7, 9, 11, 13. Now it says minus 132. But we can see easily the curve here is not very flat, means more time is needed. The distance from the green trace to the gray area is only about 2 decibels, and that's not enough. There have been glitches. We can see one here that contributes to make the phase noise a little bit less good than it should be if I didn't have any such events. And Linrad has changed a little. Now it says minus 130.7 approximately. The FSWP reports 129.75, very close to 130, and this is in full agreement with the other instruments, considering the noise level. Now you saw how it changed a little, 129.18, but more time is needed. This curvature, this should be a smoother trace when noise contributes less after much more time then. 4 hours Linrad now shows minus 131 dBc per hertz for the phase noise at 1 hertz offset. And the amplitude noise is at minus 134. And the PN2060 shows minus 131.2. And I have applied a sliding window, moving average, over 11 points. If I remove that, I get a much more noisy curve, and I have to guess where the point is, and it is at about minus 131 here. The FSWP shows minus 129.1. That is the averaged curve, the yellow trace. Without averaging, it looks like minus 130. If I try to guess where the proper curve is in here. This is a new measurement, has been running overnight for 6 hours and 47 minutes. Linrad shows the phase noise at 1 hertz as nearly minus 131. I would say 130.7 for this. The amplitude noise is significantly lower. It is 134.5 where the mouse is now. The PN2060 has been running for amplitude noise, and at 1 hertz it says maybe 130, but it has not converged. We can see the circles everywhere. So this measurement is not valid. While in Linrad, the imaginary part for the amplitude noise is far below the reported value for the real part. So I think this is a valid measurement, that it is really where the amplitude noise is. Another instance of Linrad has been running at a higher bandwidth. Here I can see the noise at 1 kilohertz. It's down here where the mouse is, and that is minus 177 or so at 1 kilohertz. And more easily to see, at 5 kilohertz, it comes at minus 180. 183. The phase noise at 5 kilohertz looks like minus 183 also. I can compress the x-axis. This means that I get a more accurate evaluation of the phase noise because more of the bins are averaged with each other in the frequency direction. And now I can say it is about minus 185. And I can compare phase noise and amplitude noise. Here is amplitude noise, and it is much easier to see now. And if I look at both of them, it is clear that the amplitude noise is 2 or 3 decibels above the phase noise at 5 kilohertz. When it comes to the phase noise, the green and the yellow curves, the FSWP is in a good agreement with what I found with Linrad as well as with the PN2060. It says in the table minus 129.3. That is within 1 dB from what I found in the other systems. The yellow trace is unsmooth, so you can see that it is not yet
well converged, although quite some time has elapsed. But the other trace, the amplitude noise, is far from what I expected. It is much stronger than the phase noise at 1 Hz offset. It was in my Linrad system at minus 134, so it should be down here. There is an error in the order of 10 decibels. When I look at 5 kilohertz, 2, 3, 4, 5, that's here, the yellow trace is the same as the marker number 2, which is 10 kilohertz, and that's minus 184. And in Linrad I saw minus 185. So that is a good agreement. But the amplitude noise was very similar. Maybe 2 decibels above, but here it is 5 decibels higher. And I don't know, it seems to me something is wrong with this unit, and it has not converged well, although the measurement time is very long. Here the noisiness has come low, so this is really noise measured by the instrument, but it's not the noise of the signal source, it's something else. Here is the current schematic diagram. I have added a resistor here. It improves the phase noise significantly by something like 2 decibels, and it also reduces the signal level, the power in the crystals and the level out here by about 2 decibels. And I don't know exactly why this improves, but I think the problem is that this way of limiting with an amplifier that goes nonlinear is not really optimum. I will study that in the next video.